Hello, my name is Freya Olsen. I'm a postdoc at the Virginia Tech Center for Ecosystem Forecasting. And in this VERA Forecasting Challenge tutorial, we're going to do a walkthrough of an R markdown simple forecasting workflow. In this video, we will follow a simple forecast workflow, as well as introducing some additional forecasting tools that give you the building blocks to start building and submitting forecasts to the VERA Challenge. Some prerequisites before we get started. You need to make sure you have the tutorial materials available on your RStudio locally, and also have your R packages installed that we're going to need. You can follow the setting up your R environment video to help get ready before we start. Before we jump into the R code, I just want to take you through what we're going to be doing. In the first part, we're going to start by reading in the targets. This is a great place to start. We need to know what the data look like. Then we will visualize the targets, investigate what data is available, what's the resolution of the data like, and also obtain some covariates that we're going to use in our forecasting. Once we have all our data, we're going to switch into the second part, which is going to be about fitting a model and generating a forecast with uncertainty. As in our previous videos, we discussed different ways to represent uncertainty, and again, I'll talk about that in the walkthrough. And finally, we will submit a forecast to the challenge and discuss some next steps when you're thinking about how to continue to build your forecasting skills and contribute to the VERA challenge. So I'm going to switch over to the RStudio window. Hopefully, if you've followed along with the setting up your R environment, you should be here having just installed some R packages, and you should be ready to go. So just to orient you, I have my R markdown window in the top left, my console in the bottom left, my files window in the bottom right, and my Git window, which I probably won't be using so much, and also my environment window in the top right. The tutorial markdown document, if you're not familiar with markdowns, you can run the code chunks by clicking the run button in the top corner. The pale gray, or depending on how you have your RStudio set up, the different colors will show you what is code and what is just text. The R markdown includes a number of text areas that kind of just describe some of the background, which you'll have seen in other videos, and that I might touch on, but I also might pass through them. But those are there for your reference when you're working through these materials on your own. So hopefully you all have the packages installed. If you don't, I would go ahead and pause the video and install those now. We're going to load the various packages that we need, including the tidyverse, lubridate, ggplot, and the VERA forecast helpers package, which is going to be crucial when we get to the end. I also should note that if you would prefer not to run the code yourself, you can navigate to your GitHub window, and the R markdown document is available in a rendered format if you would prefer. You can also just follow along and do this in your own space. Information here about the background of the challenge, which we won't go into now. Some of the submission requirements, which were discussed in the Anatomy of a Forecast video, which again you can review if you need to familiarize yourself with those. But importantly, what we're going to talk about here is what the file format is needed, the different columns here, and also how we're going to quantify uncertainty. There's a number of different distributions that are supported by the challenge, which we won't be using today, but are there for your reference, as well as links to more information on the challenge website. So to get into a simple forecasting workflow, the first thing we need to do is obtain our target data. These are available from a consistent link hosted on S3 storage. So this is going to be a predictable location for the targets as they become updated. And you can see here we're grabbing data from the VERA Forecast Challenge. And today we're going to be looking at daily in situ targets. So as I said, if you're not familiar with running R chunks, you can use the green button. You can also use inline running of code as well if you're more comfortable with that. If you want some more information about the sites used in VERA, there's a small data frame hosted on GitHub that includes the list of sites. This is quite a straightforward table with just a few columns, but describes kind of some simple information about the different reservoirs, as well as the tunnel branch, the river connecting the two systems. So first things first, let's have a look at the data. What does our data frame look like? So we have our targets data, which described in the anatomy of a forecast, has a number of columns that describe the data. It's in a long format rather than a wide format. And so we have a number of descriptor columns, including the project ID, the site ID, the date, time, the duration. This covers what time period the observation covers. So for this daily forecast, it's a P1D duration. The depth of the observation, the variable names, which are in a standardized format, including the units and the statistic, and then the observation. For this particular example, we're just going to look at one of the reservoirs, Falling Creek Reservoir, which has a 4-character code FCRE. And so we're going to filter our site list and our targets down to just include FCR. We're going to use the tidyverse functions mostly, so the filter as well as some distinct. This last line here is just to demonstrate the breadth of variables available within the challenge. At the moment for FCR specifically, there are 33 different variables. So if you're particularly interested in biological or chemical processes happening in the reservoirs, you can focus on those. Today, we're going to look at water temperature, temp C _ mean, just as a straightforward example to demonstrate the different stages of the workflow. So just to summarize, we're going to be looking at mean daily water temperature at Falling Creek Reservoir. So we're going to make sure our targets only include those data by using the filter. You can see our targets data frame up in the top right is getting a little smaller as we continue to filter down. So it's a good idea to visualize your data, have a look at how much data is available, what do the data look like, are there particular patterns that might be appropriate for a forecast model, what's the resolution of the data like, are there large gaps? So we can go ahead and run this. This is just a simple plotting function here using ggplot. And for water temperature at Falling Creek Reservoir, there are a number of different depths that are being measured. You can see that there's quite a lot of data. We have data going back to 2018. And that the data is fairly regular with just a few data gaps. At Falling Creek Reservoir, our focal depth is 1.6 meters. And so we're going to focus on that particular depth within our temperature forecasts. Now that we've looked at the data, we can start to think about what type of models might be useful to predict water temperature. So there's 3 simple examples here to kind of get you started thinking about what goes into a forecast. We could use information about current conditions at a reservoir to make predictions about what's going to happen into the future. So what's happening today is usually quite a good predictor of what's going to happen tomorrow. It's very unlikely that water temperatures are suddenly going to drop by 15 degrees. Day to day. And so that's usually a good starting point. We can also think about what the historical data tells us about the reservoir. So if you look at these plots again, you can see that there's quite a distinct seasonal cycle. We see water temperatures increasing into the spring and summer, and then cooling again into the fall and winter. And so these types of dynamics can be included in our forecast model. This might you call a climatology or a day of year model. We can also look at how the variables have relationship with other forecasted conditions. For example, we could use existing forecasts about the weather to generate forecasts about our inlet conditions. So thinking about water temperature at 1.6 meters, we're gonna again filter the targets down, and we're gonna start with this third example here, using weather forecasts to inform water quality forecasts. So in the previous videos, I introduced the different NOAA forecasts that are available, and there's some information here if you need a reminder. But we're going to be working with the stage 2 data, which is a weather forecast, an ensemble forecast of the weather, and a stage 3 forecast, which can be viewed as kind of a historical observation that we can use to train our model. These data sets are hosted on an S3 location, and to access them, we're going to use a couple of functions from the VERA Forecast Helpers package. What these functions do is they connect to those remote locations and allow you to filter and subset the data before bringing it in locally. Now, this is really useful because often we don't want all of the data available. We don't need every forecast ever produced by NOAA. We want to subset that data to what we need to run our forecast. And this is really good because it helps us limit the memory usage in R, and we can do that subsetting remotely before bringing it locally. So I'm going to talk you through the different steps of getting weather forecasts, starting with the stage 3, so this historical stacked data set. So the function we're going to use is as I said, in the VERA Forecast Helpers package, and it's called NOAA Stage 3. Nice and straightforward. And you're just going to run this and assign it to this historical weather S3 object. Now, when this might take a moment or so, depending on your internet connection, so just be a little patient if it's been a bit slow. But you can see in this top window here that the object that we assigned it to, historical weather S3, now contains an object called object containing active binding. And essentially what this function has done is created that connection to that remote location. And that's all it's done so far. It said, I want to get the data from here. It's going to wait for us to give it a bit more instruction before it brings any more data. To generate our forecast of water temperature at Falling Creek Reservoir, we're going to use forecasts from NOAA of air temperature. So I'm just going to make an object containing the variable air temperature. We're going to take our object containing active binding that we assigned in the previous part of the code chunk, and we're going to apply some dplyr functions. The first thing we're going to do is we're going to filter. And this is going to allow us to query the database that is hosted under historical weather S3. We only want temperature, and so we're going to filter by the variables that we listed, which at the moment is just air temperature, but you could add additional ones later. I'll show you where you can find information about other variables. And we also just want temperatures at Falling Creek Reservoir. So we're gonna filter here by both site and variable. And you'll notice that the NOAA weather includes the same columns as the VERA forecasts. The final step in obtaining NOAA weather is to use the dplyr function collect. And so once it's completed that query, it's going to collect that data into our local environment. Now, again, this could take a minute or so, depending on your internet connection. But once it's processed, it's going to return a data frame. You can see here, it's quite a large data frame, almost 1 million rows. And we can have a quick look at what that looks like. So as I said in the previous video, the NOAA weather is a ensemble forecast, and in the stage 3, we retain those ensembles, at least for the moment. So we have the parameter, which describes the ensemble member. We have the date time, which is the date and the time that was being forecasted. Our variable, which in this case is air temperature, the prediction given in SI units. So for this air temperature, it's given in Kelvin. The type of forecast, again, is an ensemble. And if we scroll across, we can see that there's no reference date time for our stage 3. This is kind of a pseudo observation, a historical kind of data product, and then the site that the forecast was for. So we now have this stacked ensemble of the 1 day ahead forecasts. And for model training, we don't really need the ensemble members. A kind of mean prediction is going to be good enough for training our model. And so the next step is just to aggregate these to a mean value. So that's all that's happening here. We're going to group by date, by site ID and variable, and we're going to summarize that prediction to generate a mean. So now our data set looks slightly different. Our date time is now only a date. There's no time part of that variable. We no longer have our ensemble members, but we still have our site and our variable. So it's a bit more straightforward. We have a single prediction for every day. We're going to do a similar thing to obtain our future weather. So we're going to have our historical data to train the model, and then we're going to use our future weather to run the model forward into the future. One thing to note about the NOAA weather is that the forecast only becomes available at 5 a.m. the next day. Just because of the length of time that the forecast takes to run, the data is only available once the day is over. And so if we wanted to make real-time predictions, so making forecasts today of the future, today's forecast from NOAA is not yet available. So we're going to have to use yesterday's forecast, which is kind of what is happening here. So we're making a real-time forecast. So our forecast date is today. We're going to use the NOAA forecast from yesterday to make our forecast today. So those are those first two lines. Again, it's a good idea to get these running. It can take a little time, and then I'll describe what's happening. So we're using instead now the NOAA stage 2 function. And there's an additional argument in the stage 2 function that allows you to subset based on the start date. And the start date of our stage 2 forecast that we want is yesterday. We can't get today's forecast, but we can get yesterday's. So that's what we're going to do. Again, we're doing the same filtering of the remote data set. And then we're going to collect and bring it locally. We have an additional filtering step here to only get dates that are in the future based on today. So we don't need today's forecast because we're not making a forecast of today, but we need future forecasts. So if we look at what that looks like, very similar to our stage 3 in that we have parameters. So this is again is an ensemble forecast. So it's 31 different realizations of the future. It's still in an hourly time step. The stage 2 has been interpolated into an hourly time step. Our predictions, our family, our site ID, our variable. And this time our reference date time is listed as the day before. So I'm recording this video on the 25th of May. And so whatever day you're watching this video and running that code, the reference date time for the forecast generated is going to be from yesterday. What's really useful for the forecast of water temperature is that we can use the ensemble members from our air temperature forecast to therefore include driver uncertainty in our water temperature forecasts. Using the individual ensemble members, we can then generate a water temperature prediction based on each of those individual air temperature predictions. The final thing to do is aggregate our future ensemble forecasts to a daily time step. We don't need all those hourly time steps, but this time, importantly, we're including parameter, that ensemble number, in the grouping variables so that we retain that uncertainty in our air temperature forecasts. This is a useful way just to visualize what's happening. So this is plotting both the future weather and the historical weather, and I'll just show you what's happening here. So the single black line, as I said, this is today for me in May. My historical weather goes back as far as 2020. So I have about 4 years of data, but depending on when you're watching this, it might be a little bit longer. And then you can see the multiple iterations going out into the future. And these are our individual ensemble members. And you can see as we go further out into the future, we get larger uncertainty in our forecast. So we can use the single solid black line of our historical weather to train our model and then hand over to our future weather to generate driver uncertainty in our water temperature forecast. The final step of getting all our data ready is to convert our SI unit of Kelvin into Celsius so that our units of air temperature and water temperature are on the same scale, which makes it a little bit easier to parse. So that's what's happening here. We do a pivot just to get things in a slightly easier format, but you'll see here that our data is now in a nice format for us to start thinking about a model that we can use to generate a water temperature forecast based on air temperature.